Thanks to the organizers for having me at this wonderful conference. I'm kind of an outsider to the field of quantum error correction. I'm coming more from the subfield of Hamiltonian complexity, and you'll see that in the results today and the methods we use. So really this talk is kind of a combination of those two fields, quantum error correction and Hamiltonian complexity. The first part of the title kind of is most of the quantum error correction content, and that's what I'm going to focus on for most of the talk, whereas the second part of the title, and you can read about in our paper, is really about analyzing a high-dimensional quantum spin model that can be used for adiabatic computation and QMA completeness and things like that. So I'll say a bit about that at the end if there's time. So let's see. Okay, starting off with the main idea, we're going to use what's called the Feynman-Kitaev circuit to Hamiltonian construction, which maps quantum circuits to local Hamiltonians with ground states that are superpositions over the time steps of the computation. So you start off with some quantum circuit that applies local unitary gates up to some time t. This gets mapped to what is called a history state that is a superposition over the time steps of the computation entangled with this additional new register called the clock register. So the reason that people do this in Hamiltonian complexity is that for this state, you can write down local Hamiltonian terms that are based on the gates in the circuit and enforce this state to be the unique ground state of a local Hamiltonian. Whereas perhaps the original time steps of the circuit are highly entangled and you don't know how to write down local terms that enforce them as a ground state. So this is what these kind of circuit propagation terms look like based on the gates in the circuit. So they say things like, as the clock increments from t-1 to t, you must apply the appropriate gate to connect those time steps in order to minimize the energy. So you take a sum of terms like this, and that is the local Hamiltonian. Those are the form of the local terms that we're going to call code checks. So they're non-stabilizer local checks, and a lot of this talk will be expanding on what that means. So the main idea, so all of this framework has existed for 20 or even 30 years. It goes back to Feynman. But the main idea of our work is that we take the circuit to be an encoding circuit for a quantum error correcting code. So when we that means that the output of this circuit is, is the code space, right, over some subspace of inputs, and so using this encoding circuit in this history state, we can actually make the history state arbitrarily close to the code words of the original encoding circuit, so then these kind of propagation terms will be our code checks to enforce that ground space. Here's the reference for our work. One of my co-authors, Tom, is also here at the conference, so I encourage you to talk to him about this work as well. Okay. Oh, and just in kind of this overview slide, let me say that this history state also contains some amplitude on states that are not in the code space. And that's the fundamental reason why we obtain approximate error correcting codes instead of standard bona fide error correcting codes. Okay, so for the outline, first I'm going to kind of say a bit about approximate quantum error correction and local Hamiltonians, just kind of in general. Probably mostly review for this audience, but maybe my sort of outsider perspective will shed different light on things. And then in the second part, I'll really get into describing our result and kind of the extensions and possibilities for further improvement. Okay, Okay, very generally, a quantum error correcting code, of course, encodes quantum information into a subspace of a larger Hilbert space so that it can be retrieved after the action of a noise channel. This slide is kind of setting up notation that will also apply in the approximate case. And so, of course, we all know that necessary and sufficient conditions for an encoding plus noise plus decoding procedure to achieve perfect recovery were found by Nil and Laflamme. I'll just mention that these are information theoretic conditions in the sense that they don't guarantee you can perform the recovery efficiently. And again, just preparing us for the approximate case, the Nil-Laflamme conditions, we have, kind of both an off-diagonal condition that is familiar from the classical error-correcting case that says that the code words remain far apart after errors are applied. And we also have this kind of on-diagonal condition, which is the uniquely quantum part, which demands that the code words are locally indistinguishable. Okay, so what happens if we relax the condition for perfect recovery of information? Well, this is the standard definition of an approximate quantum error correcting code, is that we require recovery of the information to fidelity 1 minus epsilon for some epsilon. So written mathematically, right, the fidelity after we've encoded applies the noise channel and decoded compared to the original state, is lower bounded. So clearly if epsilon is sufficiently small, this could suffice for a lot of purposes. Betty and Oreshkov gave necessary and sufficient conditions for this approximate recovery to be possible in an information theoretic sense. These conditions are written here. We're not actually going to use these in this talk. You may be familiar with these. Basically, it's kind of like an operator form of the Nil-Laflamme conditions with a little extra piece, and the little extra piece defines a quantum channel, and the condition you need for approximate recovery is actually about closeness of channels in the Beer's distance. So actually what we're going to do is move to easier to handle sufficient conditions to be an approximate quantum error correcting code. So the first of these is actually just kind of included for intuition. It's a result from a few years ago and has also appeared, has been mentioned in some other works. So what if we just take the Nil-Laflamme conditions and we allow that there is some epsilon on the other side? Right, remember the local indistinguishability kind of gets to the fact that if I equals j, that the CAB does not depend on I or j. But let's say that we both relax the off-diagonal and on-diagonal conditions to allow some extra epsilon piece that depends on everything. Then it turns out, pretty intuitively, that we can get an upper bound on the approximate code error in terms of these additional epsilon. One thing that was, one kind of drawback of using this condition is that the bound we get on epsilon is kind of exponentially bad in the number of encoded qubits and the distance of the code. And the reason for that is that in this version of a sufficient condition to be an approximate code, we're really only constraining the basis code words. And so when you want to talk about what happens to an arbitrary code word, it could be a superposition of exponentially many of those. And so we kind of have to take a union bound. That's the explanation for this exponential factor. So we actually want a stronger condition in order to have codes with macroscopic distance. Okay, and what the condition we use in this present work says is that what we construct explicitly invertible linear map that applies to the whole Hilbert space and maps one subspace C to another subspace C prime in such a way that basically these two subspaces, they're isomorphic and they're epsilon close together, right? So you start with a proper code space, and then you consider an isomorphic space within the same Hilbert space that is just shifted by this kind of epsilon. Then it turns out that this C prime, this kind of shifted space, will be an approximate quantum error correcting code with error parameter epsilon. So in other words, if you're in, the previous condition said that if your basis code words are close, then you're still a good approximate, or you're in approximate code. But this now gets better scaling of parameters by saying that the entire subspace is close. And I wonder, kind of an open question to throw out there, if there is a converse to this condition. Is there a sense in which every approximate quantum error correcting code is close to an exact quantum error correcting code? Probably even formalizing that correctly would take some work, but okay. Now, kind of setting up the direction we approach this work from, we all know we can associate quantum codes that have local checks with local Hamiltonians, right? And one reason to do this is that we want more in general than just information theoretic conditions about recoverability. We also want practical operational procedures to recover from errors. So in terms of practical, that might mean low weight measurements and classical post-processing should be hopefully all you need to recover from errors. And of course, the gold standard for obtaining such a complete recovery procedure, well, usually there are stabilizer codes, such as the surface code, that have local stabilizer generators. So if you have a code with local stabilizer generators, then the code space, of course, is the +1 eigenspace of a set of Pauli terms that generate an abelian subgroup of the Pauli group. So therefore, if we turn those Pauli terms into projectors, then we have a commuting projector Hamiltonian that enforces the code space as its ground space. And of course, so from the perspective of local Hamiltonians, this is kind of a restrictive class of models, these commuting projector Hamiltonians. But okay, so one of the main open questions in coding theory is whether codes with good parameters, that is linear distance and constant rate, with O of 1 local, weight O of 1 stabilizer generators exist. So the conjecture that such codes exist is called the quantum LDPC conjecture. This term, low density parity check, comes from classical linear codes and refers to the low weight of the checks and also a bounded number of checks on each qubit. But relevant to this talk is that even if we remove this restriction to be to have local stabilizer generators, and we just ask for local Hamiltonian terms in general, it remains open to show that good codes with local bounded degree checks exist. So what we really do in this work is we show that we relax this in nearly every way possible to obtain a result that is approaching what we would really want. So we don't get bona fide codes, we get approximate codes. They're good, but only up to polylogarithmic corrections, right? So instead of a distance that's like omega of n, it's omega of n over polylog n. So small corrections. And we have strictly local checks. They're 5 local, 9 local, depending on the exact version of the construction. But we don't quite achieve constant interaction degree. We have a polylogarithmic interaction degree. So here's just kind of a table, entirely work of others, or kind of summarizing the work of others in particular, if what you care about is distance, the best kind of unequivocally proven result for the distance of a CSS stabilizer code is, omega root n log n, which goes back close to, going on 20 years now. There has been some, of course, exciting work in this decade, especially by Hastings, which comes close to achieving linear distance under some conjecture of high-dimensional geometry with the CSS stabilizer code. Kind of fascinating breakthrough work in 2014 found codes with constant rate and approaching linear distance that are subsystem codes. So they are ground spaces of strictly local Hamiltonians, but they are they're gauge subsystem codes, and the Hamiltonians involved are frustrated. So what we do in this work then is we have so this tilde over the omega means that we're kind of hiding the polylogarithmic corrections. So we have almost constant rate, almost constant distance, but we have approximate codes. Okay, they're in the ground space of a non-commuting Hamiltonian, but that Hamiltonian is frustration-free. And that last point we'll actually expand on quite a bit and how it might contrast with the frustrated case. So as I was saying, at least from kind of a many-body physics point of view, the fact that stabilizer Hamiltonians are commuting and frustration-free, those are two strong restrictions. And in fact, another kind of condition to pay attention to is that, stabilizer Hamiltonians, so frustration freeness is saying that the global ground state is the ground state of each local term. But of course, this can depend somewhat on the decomposition that you use into local terms. So when we say that a stabilizer Hamiltonian is frustration free, we really mean that this frustration freeness manifests when the local terms are tensor products of Pauli's. So I'm going to abbreviate this as TPP. So code checks based on these kind of TPP terms are useful because Pauli errors must either commute or anti-commute with the local terms. So if we look at the most well-studied class of codes with local checks that are not stabilizer generators, these are, of course, stabilizer subsystem codes, and these code Hamiltonians retain TPP checks, right? The local terms are still tensor products of Pauli's, but they're no longer required to commute. Okay, but if you take both of those things together, Pauli's must either commute or anti-commute. So if you have a non-commuting Hamiltonian where the local terms are TPP, then some of those checks must anti-commute, and that is why these Hamiltonians are necessarily frustrated. As has been observed many times, this frustration is an obstacle, not an insurmountable one, but an obstacle for local error detection. And the reason for that is because the code space is not an eigenspace of the local checks. So measuring the local checks will reveal little to no information about whether you're in the code space, right? I mean, if you take an example of any subsystem stabilizer code, typically what you end up doing is measuring many, many local checks to combine them together to ascertain the value of non-local stabilizers. So one way for a code to be in an eigenspace of the local checks that do not commute is to preserve this condition of frustration freeness. But by the argument on the previous slide, this means we're going to have to give up TPP code checks. So this is how we define the term approximate quantum LDPC codes. What we mean are approximate codes that are the ground space of a frustration-free local Hamiltonian. So it's some sum of projectors that do not necessarily commute, but that the global ground state minimizes each projector individually. So our main justification for this terminology of LDPC is, besides the fact that these terms are local, we're going to show that frustration freeness implies local detection of errors, both in general, and then we get very explicit about it with our particular class of code checks. So the term kind of emphasizes a distinction between our non-commuting codes and the gauge code framework. That was our goal with that. So, you know, just to mention, another justification for considering these codes just comes from Hamiltonian complexity, where you know, we're really interested in the complexity of ground spaces that arise from local constraints, and you know, whether someone can develop practical fault-tolerant protocols is kind of a separate question. So those are the motivations for our work. So you know, what are the codes that I'm talking about? Well, this can, so it's a little tricky. So really, this Feynman-Kitaev Hamiltonian construction applies to any encoding circuit. It's an entire framework, right? So any code you want, basically, with an efficient encoding circuit. But in order to reduce the interaction degree of our checks, the number of checks acting on each qubit, we use codes with as low of a depth of encoding circuit as possible, and we want good codes, codes with the best parameters possible. And so for that, we use a result that is related to the fact that random stabilizer subspaces almost always form good codes. They form good codes with high probability. So if that's true, and we also know from the theory of T designs that random circuits produce distributions of output states that look random, at least up to the first few moments. That's kind of the intuition for this 2013 result by Winton Brown and Omar Fauzi, which combines these observations to show that random Clifford circuits with 2 local gates and polylogarithmic depth form encoding circuits for good quantum codes with high probability. So these are the codes in our construction. That is, these are the codes which we then take slightly approximate versions of and then enforce as the ground space of a local Hamiltonian. Now, since the total depth of these encoding circuits is polylogarithmic, and the Feynman-Kitaev construction applies a local check term for each gate in the original circuit, this leads to a polylogarithmic number of gates acting on each qubit, and that's why we get a polylogarithmic interaction degree. I'll mention an open question related to this at the end of the talk. So, okay, so those are the codes. Keep those codes in mind. And imagine plugging those encoding circuits into this history state here. And so what you'll see is that this is a superposition of a whole bunch of states, right? At t equals 0, we really just have the input states to the circuit, which are just product states. They're not in the code space. And for larger t, you know, we eventually have applied all the gates in the encoding circuit. That is, for t equal to the final time, that part of the superposition is exactly in the code space. But of course, we don't want just we don't want a tiny part of our state in the code space. We actually want the bulk of our state to be in the code space, or the majority of the amplitude, I mean. The standard trick for doing this is to pad the circuit with identity gates. So for example, you know, so here's kind of a picture of what I'm talking about. In the very beginning, you have something that doesn't look like the code space at all. As you apply gates, you get closer to the code space, and eventually you're in the code space. Does anyone have another pointer? I think this just had a battery issue. It's okay. So maybe I can kind of use the mouse here. So then you're entirely in the code space. And then what you'll do is you'll just kind of continue applying identity gates in this superposition to increase the amplitude of the state that overlaps with the code space itself. Sure. Okay, so that is one way to increase the overlap with the desired code word. But actually, we use kind of a more sophisticated way to do this that allows us to tune the error of our approximate code to be whatever we want. And we do this by using what we call modified circuit to Hamiltonian constructions. So these are, thank you, these are versions of the circuit to Hamiltonian construction that instead of having a uniform amplitude over the time steps of the circuit, allow for some non-uniform amplitude. And so the kind of distribution that we use looks like this, right? So we actually want 1 minus epsilon of the amplitude to be concentrated on the final time step, and we take the other epsilon fraction of the amplitude and spread it out on the other time steps, right? So now, maybe as you start to look at this, you'll see this is really, this matches the code space. These are the code words, and here's just kind of a little bit of noise that tags along that makes this an approximate code. So all this looks like mathematically is we've kind of shifted the uniform normalization to a time step dependent distribution over the time steps of the circuit. And I'll just mention that this kind of these kind of biased history states could also be useful in other contexts like universal adiabatic computation, where these states are used. Our technique for kind of generating this desired distribution is relatively standard. So basically, it is related to it's related to Markov chain techniques. So given any distribution on this state space of time steps, we can construct a Markov chain with metropolis transition probabilities that has its stationary distribution corresponding to the distribution pi of interest. And this Markov chain satisfies a detailed balance condition, as metropolis Markov chains always do. Sometimes these are called symmetric Markov chains because they are mapped by a similarity transformation to symmetric matrices, i.e. Hamiltonians. So basically, using these Markov chain techniques, then we can construct a Hamiltonian with the ground state matching the desired distribution over the time steps. Maybe that's kind of an aside, but that's the technique we use. So using this technique, again, it's any desired distribution, so we can even take the error to be exponentially small, the approximate code error. We do that by putting nearly all of the amplitude at the final time step, okay? So what is the trade-off? Why wouldn't we just kind of do that once and for all? Well, you know, we have a non-commuting model, so let's think about what our local terms really do. They enforce containment in the code space by demanding the code word be connected by the appropriate encoding circuit back to the initial product state. And if we put less weight on the early time steps, then we make the energy cost of corrupting those time steps very small, right? So basically, if we put too much amplitude on the final time step, then what we're allowing is that there are states outside the code space which have an exponentially small energy relative to the local checks. So what are the local checks really checking then? Kind of now that we have this framework, it's interesting to explore the ultimate limits of it. And actually, well, actually, before I get there, let me kind of use it to state the result. So what I was just kind of pointing out is an issue we often don't have to deal with, because if we have commuting projector Hamiltonians, there's always a constant spectral gap to states outside the code space. So in the non-commuting setting then, this example shows the importance of lower bounding the spectral gap to states that are outside the subspace, right? So how should we feel about codes with local checks but an exponentially small gap? You know, maybe it's okay, but you'll need some other reason to justify why that's okay, right? Otherwise, it's a very weak form of enforcing the code space. So basically, we can analyze the spectral gap of these Feynman-Kitaev Hamiltonians, even in this modified case, using some standard Markov chain techniques. And the result that we obtain by combining this framework with the random encoding circuits from the result by Brown and Fauzi. So what we get then is that for For any code error epsilon, which may depend on the number of physical qubits, that's what I mean by this subscript, may depend arbitrarily as a function, there exists this NKD epsilon approximate QLDPC code with a, actually you can have a 5 local code Hamiltonian on qubits that has these parameters. The number of encoded qubits is linear up to polylogarithmic corrections. So is the distance, and then now the gap actually goes down with both the code error and this extra n to the -3 factor. So if you take the code error to be inverse polynomial, then the spectral gap is no smaller than inverse polynomial. So you might be hopeful that you can do even better than this in this framework, but we actually have some stuff that precedes this work that kind of gives a no-go about this. Because this trade-off between wanting a large amplitude on the final time step and also protecting the input so that we can have a large spectral gap, this also occurs in all the other contexts where this construction is used, that is Hamiltonian complexity and universal adiabatic computation. So we already had a no-go theorem, which essentially says that if you have a tridiagonal matrix that is a Hamiltonian that has this kind of nearest neighbor on a line connectivity on the clock register, then the product of the spectral gap of the Hamiltonian with the minimum amplitude on either the initial or final time step is, at most O of t to the -2. So basically this is kind of constraining everything you want to do. You want the gap to be big and you want big amplitude on the input and output, but you can't have it all. This product can't be order 1, for example, like you would really want. So basically using this modified construction, we've kind of pushed it to the limit of code error and spectral gap. Okay, great. So this frustration freeness then means that any error that produces some component outside the code space is detectable in principle by measuring the energy of the local terms acting on that qubit, because you should be in the ground space of all those local terms. Now those local terms do not necessarily commute, but since we have polylogarithmic interaction degree, we can do so this is just one thing you could do. You could do a weight polylog n measurement of all the terms that act on a particular qubit simultaneously. And if there's an error on that qubit, then there must be some non-zero energy with respect to all those terms. Okay? But the fact that our local terms are not TPP, not tensor products of Pauli's, means that the component of the state outside the code space after an error could be much smaller. So what happens then, so imagine that you only have this inverse polynomial probability of this inverse polynomial expectation value with respect to these local terms. Then when you measure it, you might actually just get 0, right? Even though there was some small energy there. Now, if you're lucky, getting that 0 projects you back into the code space and fixes the error. But in general, it's going to start spreading around the error uncontrollably. So kind of one idea for fixing that is to use a Hamiltonian complexity technique, which is the Marriott-Watrous procedure for amplifying the acceptance probability of a QMA verifier circuit when you only receive one copy of the witness. So if an error occurred on a subset of qubits, and we're going to look at those local checks, the idea is to amplify the probability of seeing that error to approach 1, right? Because basically, if there's an error there, you don't want to mess up and conclude that there is no error. So you amplify the probability of seeing it. And so what we do in the paper, I'll give a little bit of the flavor of it. We analyze all possible cases of Pauli errors acting on our system, and we show that there is always at least one local term, so actually strictly k local term, with energy inverse polynomial in n after a Pauli error has been applied. And then this expected energy can be amplified by a polynomial depth quantum circuit to see the error with probability approaching 1. Okay, so that's a hint that local error detection is possible. That is, an error acts on a qubit, then some circuit on a region, a constant size neighborhood of that qubit, can see the error with probability approaching 1. Now, this amplification circuit is not even close to being fault tolerant. The world wasn't built in a day, but just the point is that it is acting locally on the system. Yeah, so that's kind of what the standard amplification lemma looks like. Okay. So what we do then is we let this circuit, this amplification circuit, yeah. So basically, you're going to take the original system, you're going to append some ancilla, you're going to apply a circuit whose depth depends on the probability of failure that you ultimately want. And so of course we're going to have that circuit amplify the measurement of our local projector terms. The initial probability then is inverse polynomial, and in fact, it scales inversely with the circuit size, so we can use this lemma to amplify the detection of the error to probability approaching 1. So we have that in place, but then we now have to argue then for this inverse polynomial energy, that is that the energy is not exponentially small. So one way to do that is using the spectral gap result. But for reasons that'll be clear in a moment, we also do some more explicit calculations. That is, so the spectral gap refers to the lowest energy of states that are outside the code space, but this could be the energy produced by local errors acting on the system could actually be larger in general than this kind of non-local excited state. And so what we show just kind of explicitly case by case is that these, if we have some kind of Pauli error applied to the system, then basically it has to appear in at least one time step of this superposition. And this is the reason that it gets an energy like 1 over t, which is better than this 1 over t cubed or so on that would come from the spectral gap. So local errors actually have a larger energy, which kind of matches the intuition. Okay, it's getting a little short on time, so one thing I want to say is that in the title we talk about space-time circuit Hamiltonians. And the reason we do this is that it actually increases this energy of a local error. So what a space-time circuit Hamiltonian is it associates a separate clock register with each physical qubit. So instead of having one clock, you have many clocks. And this kind of makes the analysis a lot more difficult, but it greatly boosts the detection of local errors. Instead of 1 over the circuit size, it becomes 1 over the circuit depth. This is kind of an exponential improvement because our encoding circuits have polylogarithmic depth. So that is the reason that we use these much more complicated space-time Hamiltonians in our full version of the construction. Okay, kind of summarizing here with some open questions. So our interaction degree of our Hamiltonian comes from the depth of the encoding circuit. So we know that deterministic constant depth circuits cannot produce codes with distance that scales with system size. But we also saw in Robert Koenig's talk yesterday that it is possible to use post-selection to have macroscopic distance in constant depth, although not necessarily linear distance, because that is related to a surface code. So, is it possible to have good codes in constant depth with efficient post-selection? Then we might be able to extend the result we have here. Some natural questions, do these codes have transversal gates or efficient decoders? those questions probably require de-randomization. Remember, this is a framework that you can plug a variety of codes into. Now, more general error models. The restriction to Pauli errors is actually really justified when you have checks that are tensor products of Paulis. So kind of by moving away from that condition, it opens up some questions about what is the appropriate error model. Now, because these non-commuting terms might be hard to use in a complete fault-tolerant protocol, you could also think of them as using them in passive error correction, Hamiltonian error suppression. So do these codes have macroscopic energy barriers or self-correction? Can you even define that for a non-commuting model? And because this construction is related to universal adiabatic computation, can it also make that thermally stable as well? Thanks.
Okay, we have time for a few questions. So I can start with one actually. So
sure.
It looks like this procedure to construct like LDPC codes out of some encoding circuits seems very general.
Yeah.
So I was wondering if you like looked into like specific like families of codes which don't actually have like local checks. For example, like holographic error correcting codes with like one encoded qubit, and like maybe you found something interesting.
Yeah, I agree. It's completely general, and so really what we're taking is codes that already exist, and developing local checks. That kind of gets to this question that some of the next steps from an error correction point of view, we probably want to consider de-randomization. So yeah, I think that'd be interesting to consider. I'm not sure I know any holographic codes with such explicit encoding circuits, but maybe we can talk about that.
Thanks for the talk. So I think I followed most of it, except I got a little bit lost when you were talking about performing a measurement and amplifying the probability of getting a certain outcome.
Yeah. So let's think of the context.
It was a big lemma, and I didn't.
Right. I just thought this was kind of a cool idea if people want to consider error correction in a non-commuting setting. So if you think of QMA completeness, that is quantum Merlin-Arthur verifier circuits, you have some witness that is handed to you that you need to verify, see if you apply a circuit and it produces the output 1. But you only get one copy of this witness. And you're afraid of the case where it should output 1, but you have some probability of 0, so you end up getting a 0. And so, in this previously established case, there's a solution to this problem. That is, if your probability of obtaining 1 is exponentially small, then it remains, if it's 0, it remains 0. If it's exponentially small, you amplify it up to 1, basically. So it's, you change the circuit that you use to, right, so you have something that doesn't quite say there's an error with probability 1, but it has some non-zero probability of catching the error, and you want to amplify that to probability 1 so that you don't accidentally conclude there's no error, because if you did that, you would spread the error around in general.
Yeah, I guess I follow the statement, but I can't quite picture how it works. But maybe try to figure it out later.
I think it's hard to explain. Yeah, thanks.
Any other questions? Actually, I have like one super quick question. So like,
sure.
There was this slide about a relation between the approximate Kunill-Laflamme condition and like its relation to this Benny-Rishkov condition.
Yeah.
I know that you do need an exponential factor that depends on the size, the number of encoded qubits, but it wasn't clear to me why you need the dependence on D.
That's a really good question. I would love to see that removed. We just weren't able to do it in the calculation. And so basically it comes from taking a union bound over all the Krauss operators. But we aren't able to use the fact that they kind of form the identity, right? Which is probably what would fix that, but it's not clear in the proof how to do that.
Okay, thank you.
Thanks.
Okay, let's thank Elizabeth.